Hello all, welcome back to my YouTube channel All About VLSI. Hope you're all doing good and I hope my voice is audible and my screen is visible. Good evening everyone. So this is the day 3 of analog electronic circuits, right? So we'll discuss about so today's agenda is VI characteristics of forward and reverse bias in PN junction. Okay. So in previous session we have discussed about forward bias and reverse bias of PN junction diode. So in this session we are going to discuss about the VA characteristics, voltage to current characteristics of forward and reverse bias, okay, of PN junction diode. Okay, let us start today's session. And before starting the session, make sure that you subscribe to our channel All About VLSI. Please do subscribe if you haven't yet subscribed. Okay, yeah. So VA characteristics of PN junction diode. V is nothing but voltage. So we are going to see voltage versus current characteristics versus current. Okay, so we are going to see the relation between the voltage and current characteristics of the PN junction diode in forward bias and reverse bias. Okay, so this is the specific VA characteristics of PN junction diode in forward bias condition. Okay, so this is on the y-axis it is IF, which means forward current, and this is in milliamperes, and this is forward voltage. Okay, this is forward voltage. Okay, so this graph represents the relationship between the dependence of voltage and the current. Okay, we will come to this in a minute. So here the image shows the forward VA characteristics of a PN junction diode. What is the PN junction diode is in? It is in forward bias condition. Okay, so I will draw it. So this is our PN junction diode. This is our PN junction diode. This is anode and this is cathode. So how to forward bias this particular PN junction? We will apply positive to the anode and negative to the cathode. Negative of the power supply to the cathode. Positive is applied to the anode and negative side is connected to the cathode. Okay, so this is how we will make the forward bias connection of PN junction diode. Okay, now so the image shows the forward VA characteristics of a PN junction diode. In forward bias condition, the voltage, that is the voltage VF, here not VFV, it is voltage VF is applied across the diode in such a way that P type side is positive and the N type side is negative. Okay, that is we have already seen. Now let's see what are all the regions in this particular graph. Okay, so the first region is low voltage region. Okay, so the first region is low voltage region. So initially as a forward voltage, it is not. Initially the forward voltage VF, okay, is increased from 0 and the current which is IF through the diode remains small. Okay, from the graph if you observe here, this is on the x-axis we have forward voltage and the y-axis we have forward current. The same thing we have discussed in our previous session. We have discussed in the form of theory, but in this session we are discussing in with the help of the graph. That's it. Okay. Now, so here if you observe, the voltage, forward voltage is starting from 0 volts and it is reaching some point here. Okay, so up to this point it is called low voltage region. What it is called? Low voltage region. It is called as low voltage region. That is, the voltage is starting from 0 volts and it is reaching some point. Okay, so this region is called low voltage region. So initially as a forward voltage VF is increased from 0, the current IF through the diode remains very small. Okay, here we can observe the voltage is increasing from 0 to a particular point. If the voltage is increasing from 0 to particular point, we can observe the current is also increasing from 0 to some particular point exponentially. It is starting from 0 to some point. Okay, it is reaching to some point exponentially. The curve you can see it is in exponential in nature. Okay, the current is very small in this particular region. In the low voltage region, the current is very small, that we can observe here. Okay, so since the voltage is very small, the current is also low. Okay, this, what is this? We are discussing about forward bias. Okay, do remember this, we are discussing about forward bias diode. Okay, now, so that is what it is written. Initially, as a forward voltage Vf is increased from 0, the current If through the diode remains very small. Okay, initially the current is very small. So this is because the applied voltage is not enough to overcome the depletion region's potential barrier. Okay, we have discussed in our previous session, right? Threshold voltage, V threshold, or barrier voltage threshold. Okay, so since our external voltage initially it is less than our threshold voltage, since it is less than our threshold voltage, then what happens? More number of electrons or holes cannot pass this depletion region. So what happens? The current, that is forward current, is very less initially. Since our external voltage is less than the threshold voltage, our current remains small initially. That we have discussed in our previous session also, right? So that is what it is written here. So this is because the applied voltage is not enough to overcome the depletion region's potential barrier. For silicon diodes, this voltage is, cut-in voltage is typically 0.7 volts, and for germanium 0.3 volts. Okay, until the V external reaches 0.7 volts for silicon and 0.3 volts for germanium, until the external voltage reaches this particular value, the current will be small itself. That is, the current flowing through the diode will be small enough. Okay, that is what we have discussed in our yesterday's session also. And from here, the graph also, if you observe, up to here, that is the threshold voltage is reached, the current is small itself. So up to here, the current is flowing, a very small amount of current is flowing through the diode. Okay, now threshold voltage. Next point is threshold voltage. So the forward voltage, it is not VF, it is VF. Okay, once the forward voltage Vf reaches the threshold around 0.7 volts for silicon, the depletion region starts to shrink significantly. This we have seen yesterday, what is happening if it reaches the threshold voltage, and what happens if it crosses the threshold region, the external voltage, what happened, that we have seen yesterday's session also. Okay, allowing current to flow through the diode. Beyond this point, any small increase in Vf results in a large increase in the forward voltage If. Okay, so if external voltage increases, that is in our case Vf increases above 0.7 volts for silicon or 0.3 volts for germanium, if this cut-in voltage has been exceeded, then what happens? Then there will be a large increase in the current If. Okay, through the diode, that is forward current will be increases largely. From the graph also, if we observe, so after reaching this threshold voltage somewhere here, let's say this is 0.7 volts. So after crossing this voltage, you can see the current is increasing drastically. Okay, the current is increasing drastically after this 0.7 volts. When Vf, that is forward voltage or external voltage, reaches, or it increases greater than 0.7 volts for silicon and 0.3 volts for germanium, after this particular voltage has been reached, that is a cut-in voltage has been reached, then the current increases rapidly. Okay, that is what we have seen, and that is the threshold voltage. So beyond that point, any small increase, so after that point, what happens? If there is any small increase in voltage also, like if there is a point increase in voltage also, there will be a rapid or drastic increase in the value of the current. Okay, so after the threshold voltage, even if there is a small change in the voltage value, there will be a drastic change in the current value. Next comes the high current region. So after the threshold voltage, the diode current increases exponentially with a relatively small increase in the forward voltage. So the steep rise is seen in the curve, becomes almost vertical in the high current region. So in this region, the diode conducts heavily and the forward voltage drop relatively stable even if the current increases. So if you observe the graph, so here after a certain point, what happens? The current increases rapidly and it becomes steep. Okay, so it increases heavily. So even if the external voltage is constant, but this current value will get increased more and more. So it will reach a steep. Okay, so even if there is a small increase in small decimal point, 0.2 0.3 volts increase also, there will be a huge increase in the value of the forward current which is flowing through the diode. So this is after high this is after passing the threshold voltage. Okay, that is what it is called as high current region. Okay, now, so this is about the VI characteristics of forward bias diode. Okay, so initially what is happening? So initially, if the voltage external voltage is 0, there is no voltage applied, then the forward current flowing through the diode will be equal to 0. And if the forward voltage increases, that is, it is increased, but it is less than the threshold voltage. That is, it is less than the threshold voltage, that is 0.7 volts for silicon, or 0.3 volts for germanium. If it is less than the threshold voltage, the current value will increase lightly, small. There will be a small increase in the current value. There is no drastic increase. Okay, so if the voltage value increases but it is less than the threshold voltage, then the current value increases in a small manner. Okay, there will be a small current. But if the voltage increases beyond a threshold voltage, then the current value gets increased rapidly. And at a certain point of voltage, if there is any small change in the voltage value also, there will be a huge change in the current value. That is what the graph is being that is what the VI characteristics of a forward bias diode. Okay, so this is about forward bias condition of a this is about VI characteristics of a forward bias PN junction diode. Okay, now let us see what is meant by dynamic resistance. Okay, I hope you are aware of what is meant by resistance. So in general, resistance is nothing but the obstruction which is applied to the flow of the electrons or flow of the current. So if the resistance is more, then there is less current flowing through that particular device. Okay, so if the resistance is more in the diode, then there will be less current flowing in the diode. If the resistance is less, then current will be more. Okay, so resistance is nothing but, so in general, it is given by voltage by current. Okay, so here R is inversely proportional to I. Okay, R is inversely proportional to I. Right, we know this already. So if resistance is huge, resistance increases, current decreases, and resistance decreases, then current increases. This we already know. Then what is this dynamic resistance? The word dynamic itself indicates that the resistance is increasing and decreasing dynamically as the graph proceeds, or as for external voltage increases or decreases, the resistance value is getting increased or the value of the resistance decreased. So this dynamic behavior is called dynamic resistance. This is called as dynamic resistance. That is, the value of resistance is increasing and decreasing dynamically. What is that? We will see. So the dynamic resistance, it is denoted by RD, also known as incremental or small signal resistance, is the resistance of the diode at a particular operating point in the forward bias region. So it is defined as the slope of VI curve at a given point. So we will see that how to calculate this dynamic resistance at a particular point. Now, so at this particular point, if we observe the value of our voltage, so at this point and this point, we will consider 2 points of this curve. Okay, so this point and this point. Okay, so at this particular point, the voltage, let's say it is V1, and here let's say V2. Okay, and so current corresponding to this voltage V1, which is nothing but, let's say it is I1. Okay, current corresponding to voltage V1 is nothing but I1, and current corresponding to V2, from this graph we can observe it is I2. Okay, then how to calculate this dynamic resistance? Let me erase this. Then how to calculate this dynamic resistance, or RD, which is nothing but V2 minus V1 divided by I2 minus I1, which is nothing but change in voltage by change in current. Okay, V2 minus V1 by I2 minus I1, delta V by delta I. So here from the graph you can observe the voltage is more. Okay, voltage difference is more. That is, it means what it indicates, there is a huge increase in the voltage, that is V1 and V2. Between the V1 and V2 there is a huge gap. Okay, that means voltage has been increased more. But on the y-axis, if you observe, there is less gap between I1 and I2. That is, there is only small increase in I1 and I2. Okay, there is a huge difference. V1 and V2 has huge difference. That is, there is a huge increase in the voltage of V2 from V1. Huge difference. We can see this from the graph. And I1 and I2 has a very less difference. That is, it indicates that there is a small increase in the current. So if there is a large increase in voltage, but there is a small increase in the current, that is what it is written here. So here from the formula we can observe, RD is equal to delta V by delta I. Okay, so from here what we can observe, dynamic resistance is directly proportional to change in voltage. Okay, dynamic resistance is directly proportional to change in voltage, and it is inversely proportional to current, change in current, inversely proportional to change in current, 1 by delta I. Okay, so if the dynamic resistance is more, then the flow of current is less, right? That is what it is written, right? Or if there is more change in voltage, then this dynamic resistance, so it is directly proportional to it, right? Yeah. Now what we can observe, how to calculate this dynamic resistance, it is clear, right? RD is equal to delta V by delta I. Now, so here dynamic resistance, it is what it is written here. Okay, now what is the importance of this RD? So dynamic resistance is important in AC circuit analysis because it indicates how the diode responds to small AC signals when biased at a particular DC points. Okay, that is the importance of our dynamic resistance. But we will see one more thing here. So here, if you observe carefully, there is at this point there is huge increase in the voltage, but there is only a small amount of current. That means in this particular portion, resistance is very high, because there is a less amount of current flowing in this region. Here the gap only you can observe, right? There is a huge amount of voltage increase, but there is a less amount of current, which means RD is very high. The resistance which is offered to the current by the diode is very high. That is before the threshold voltage. But after the threshold voltage, what it is happening, from here we can observe the current is increasing rapidly. Okay, but for only if you observe, let's say this is V3 and this is V4, there is only a small increase in the voltage from V3 to V4. But in the current, if you observe, the current corresponding to V3 point, let's say it is I3, and the current corresponding to the point V4 is, let's say, I4. So for a small increase in the voltage from V3 to V4, there is a huge amount of increase in current from I3 to I4. That means the value of RD is getting decreased in this particular region after the threshold voltage. After the threshold voltage, what it is happening, RD is getting decreased. Okay, the resistance offered to the current by the diode is getting decreased. I will write it here somewhere. So before threshold voltage, dynamic resistance, that is diode, which is diode, the resistance offered by the diode to the current is more. But after the threshold voltage, the resistance, this is R, not V. Okay, the resistance offered by the diode to the current is less. Okay, you can observe here only how the resistance is being changed before and after the threshold voltage. So that is why it is called as dynamic resistance. I hope it is clear, right? Now, so this is about the dynamic resistance in the forward bias condition. Now let's see the reverse bias condition. So this is the VI characteristics of a reverse bias diode. Okay, this is a VA characteristics of reverse bias diode. Okay, PN junction diode. So initially, if you observe, when the voltage is zero, the current is also zero. And if the value of voltage is increasing, but the current is stable, okay, you can observe from the graph, the voltage is represented on the x-axis. This is reverse bias voltage VR, and reverse current is measured in IR across y-axis. Okay, y-axis this is, and this is x-axis. Okay, so if you observe the voltage value, it is being kept increasing. Okay, but if you observe the current value is still stable, that is, it is almost zero. Only a small amount of leakage current will be flowing. Okay, so if you observe, until a point called breakdown voltage, until a point called breakdown voltage. So until the voltage reaches this particular value, the current will be almost equal to zero. And after the voltage reaches this breakdown voltage, the current value starts increasing abruptly. Okay, it will go on increasing abruptly. Okay, so when the voltage reaches this breakdown voltage, it will increase rapidly. So this is how the diode works in a reverse bias condition. Okay, this also we have discussed in our previous session. So this image shows the VA characteristics of a PN junction diode in the reverse bias. When a diode is reverse biased, the voltage VR is applied with the N-type side connected to the positive terminal and the P-type side to the negative terminal. Right? The connection also we have seen, right? Once again I will draw it. This is the negative side of the power supply, which is connected to the anode, and the positive side which is connected to the cathode, positive and negative. This is reverse bias. So initially, as a reverse voltage VR is applied, only a very small amount called reverse leakage current IR flows, that we have seen from the graph, and flows to the diode. The current is typically in microampere range and is due to the minority carriers. The depletion region widens and diode acts almost like an open circuit, blocking most of the current flow. This already we have discussed in our theory session, in our previous session. So if you haven't watched that class, please go and rewatch that, so it will be more clear. Okay. So what happens if VR increases? IR remains almost constant. From the graph also we have seen, and it will be very small, indicating that diode is in a reverse blocking state. But this region continues up until a certain critical point known as breakdown region. Okay, from the graph we have seen that, right? So until this point, which is called as breakdown point, it remains constant, and after reaching this point, the current increases rapidly. Okay, so this is about the explanation of breakdown region. I think it is no need, that we have already discussed in our graph only now only. Okay, and this one point, knee point, this we will discuss. The point where the reverse current suddenly starts to increase significantly marks the knee of the curve, indicating onset of the breakdown. Okay, the point where the current starts flowing suddenly, that point is called as knee point. Here it is written, right? So that point is called as knee point. So what are the key points or key takeaways from this? So reverse leakage current or IR remains nearly constant before the breakdown and after the breakdown. So breakdown voltage is specific characteristic of each diode and depends upon the doping level. And reverse breakdown is not necessarily destructive if the current is limited. So always this reverse bias current is not destructive. So it can be. It is. If the current is limited, and the special diodes like Zener diode, which we will discuss in our upcoming sessions, which are designed to operate in breakdown safely for voltage regulation purposes. Okay, that we will discuss in our upcoming sessions about the Zener diode. Okay, so, and in summary, if we see the reverse bias condition, a diode ideally blocks the current flow until the breakdown voltage is reached, and at this point it begins to conduct the reverse direction, allowing a large reverse current to pass through. So that is what we have seen in this session. Yeah. So that's all for this session. If you are having any doubts or queries, you can post me in the chat. I will try to help you, or else we can end this session. Okay. Thank you. And don't forget to like, share and subscribe to my YouTube channel, All About VLSI. Okay. Thank you.